Welcome, my friends! In this video, we'll be discussing section 3.4, Numerical Summaries of Variability. Recall that variability relates to how spread out the numbers are in a dataset. We have previously discussed the range and the IQR, or interquartile range, as measures of variability. The range is simply the maximum minus the minimum, which measures the distance from the smallest to the largest value in your dataset. The IQR, or interquartile range, is the distance between the third quartile, or 75th percentile, and the first quartile, or 25th percentile. You can think of the IQR as the range of the middle half of your dataset, which is also the length of the box in the box plot. These measures of variability are very limited as they each only consider two different numbers. We would like a measure of variability that considers every single number in the dataset. Introducing the standard deviation, which has, admittedly, a little bit of an intimidating formula. The standard deviation for a sample is going to be represented by the lowercase letter s. To find the standard deviation, we will take the sum of the squared deviations, each value minus the mean squared, divide by the sample size minus 1, and then finally, we will take the square root. The standard deviation is the most common way to measure spread or variation in a dataset. The way I would like you to think about the standard deviation is as the average distance from each observation to the mean. Technically, this is a little bit of a simplification, but it's a good common way that we can think about what the standard deviation is telling us. Let's look at an example. Here's a dataset that has 5 values. We have 5, 5, 6, 7, and 12. Now, to calculate the standard deviation, I usually make a table that has 3 columns. The first column will contain all of the data values, which we represent with the letter x. The second column will contain all of the deviations, which is the inside of the parentheses in the standard deviation formula, x sub I minus x bar. The last column is each of the deviations squared, so that's x sub I minus x bar squared. The first thing we should do is calculate the sample mean, x bar, and the sample size, n. The sample mean can be found by adding up all the data values together and dividing by 5. If you do that, you will get 7. The sample size is just the number of data values that we have, which is, in this case, 5. Next, what we can do is we can find the deviation of each value, which is just taking each value and subtracting the mean, which is our second column here. So we can take our first data value of 5 and subtract the mean of 7. 5 minus 7 is equal to negative 2. This tells us that the value of 5 is 2 units below the mean of 7. We'll have the same result for our second row. 5 minus 7 is negative 2. And for the third row, we will have 6 minus 7, which is negative 1, 7 minus 7, which is 0, and finally 12 minus 7, which is 5. This column is simply taking each data value and subtracting the mean of 7. Remember that if we sum up all of the deviations, which are these values in the second column, we're always going to get 0, because the mean is the balancing point of a dataset. Next, we can take each of these values and square them. Be very careful though. If we have any negative values, we'll want to type these in parentheses first to make sure that we have the correct order of operations on our calculator. Negative 2 squared is the same thing as negative 2 times negative 2, which is equal to 4. Negative 2 squared again is equal to 4 again. Negative 1 squared is equal to 1. 0 squared is just equal to 0. And 5 squared is equal to 25. Now we have found all the values in x sub I minus x bar squared. So the next step is to sum all of these values up. Remember, this symbol is the Greek uppercase letter sigma, which tells us to sum up or add up whatever's in front of it. So now we're going to add up all the values in this last column, which is x sub I minus x bar squared. If we add up all these numbers, 4 plus 4 plus 1 plus 0 plus 25, we will get 34, which is the numerator of our formula. All right, now that we got the hard part out of the way, all we have to do is complete the formula. The next thing we need to do is divide by n minus 1. Since n is 5, the number of data values that we have, n minus 1 will be 4. So we can take 34 and divide by 4 to get 8.5. Note that there's a special symbol used to represent this value before we take the square root. This is s squared, which is called the variance. The final step is going to be to take the square root. The square root of 8.5 is approximately 2.92. This means that on average, the observations are about 2.92 units away from the mean of 7. And we are done. I know this can seem like a lot the first time you see it, but I promise once you've practiced a few times, it's not really too bad. Now, one final thing I want to note about the standard deviation calculation is that similar to the mean, the standard deviation is very sensitive to outliers. We may or may not consider 12 to be an outlier here. It's a little bit larger than the rest of the values in the dataset, but not too much larger. Look what happens when we find the deviation and square it. The deviation for 12 is 5, meaning that 12 is 5 units above the mean. When we square this value, we get 25, which ends up getting added to the numerator of our formula. The value of 12 added more to the numerator than any of the other values combined. So we can conclude that if we have outliers in our dataset, that's going to contribute quite a bit to our standard deviation formula. So we would say that the standard deviation, similar to the mean, is sensitive to outliers. Here's the standard deviation for 3 different datasets which actually all have the same mean of 7. So kind of the idea here is to show that even if we have the same measure of center or the same mean for 3 datasets, we can have quite a bit of a difference in terms of the standard deviation or variation. The first dataset has no variation in the numbers. All the numbers are exactly the same. They're all 7. So therefore, it would make sense that our measure of variation, the standard deviation, would be 0. On average, these values are 0 units away from the mean of 7. In dataset 2, the numbers are a little bit more spread out, so it makes sense that the standard deviation is a little bit larger. Finally, dataset 3 has the most spread of all the datasets, so it makes sense that the standard deviation here would be the largest. Okay, next I'd like to remind you of a few key terms that we introduced in previous videos. A statistic is a number that describes some aspect of the sample. A parameter, on the other hand, is a number that describes some aspect of the entire population. So statistics describe samples, and parameters describe populations. We had a table in a previous video that described some of the common measurements that we might use, and the symbols that would be used for statistics versus parameters. And we're going to add on to that table in this video. So recall that if we calculate the mean, and the mean is based on a sample, meaning it is a statistic, then the symbol we're going to be using is x bar. On the other hand, if we have a mean based on all the data in the entire population, we're going to use a different symbol. We're going to use the Greek letter mu. If we calculate a proportion, and it's based on a sample, meaning it's a statistic, then we're going to be using the lowercase letter p with a hat on top, which we call p hat. If we calculate a proportion based on the entire population, then we're going to be using just the lowercase letter p. And now we can add on to this chart. If we have the standard deviation based on a sample, we're just going to be using the lowercase letter s, as we saw in the previous few slides. Now, if we have the population standard deviation, we're actually going to be using the Greek lowercase letter sigma, which looks something like an O with a little hat on top. Not the same type of hat as p hat, but kind of, I guess you'd say, a cap or maybe a bill on top. And then we have the variance, which is really just the standard deviation squared. This is the value you get before you take the square root in the standard deviation calculation. And appropriately, we just use the exact same symbols, but with the square. So s squared is the sample variance, and sigma squared is the population variance. It's very important to remember that you can always get to the variance or standard deviation by doing one or the other operation. So if you'd like to find the variance and you have the standard deviation, all you have to do is square the standard deviation. And on the other hand, if you'd like to find the standard deviation and you have the variance, you can just take the square root of the variance. In most cases, we're going to be dealing with the standard deviation, but for some mathematical calculations, it's nicer to have the variance. Now, it turns out that the population standard deviation has a slightly different formula than the sample standard deviation. Here are the formulas for both standard deviations. If we have the sample standard deviation, which we did in the last few slides, we're going to be taking each value, subtracting the sample mean, squaring it, dividing by n-1, and then taking the square root. For the population standard deviation, there are two main differences. One is we're going to be using the population mean rather than the sample mean. That should make a lot of sense. Since the population standard deviation is based on the entire population, it makes sense to use the population mean rather than the sample mean. The other difference is we're going to be dividing by capital letter N, where capital letter N is the population size rather than the sample size minus 1 that we do in the sample standard deviation. Now, you might be wondering why n minus 1 here and just n here. Well, the details of that are a little bit beyond this class, but just suffice to say that usually when we're calculating a sample standard deviation, the idea is we would like that sample standard deviation to be as close as possible to the population standard deviation. And it can be proven mathematically that the sample standard deviation will be a better estimate of the population standard deviation if we divide by n minus 1 rather than just n. Okay, so here are the standard deviation and variance formulas all on one slide. Here are the standard deviation formulas from the previous slide, and the variance formulas are really just the same thing, but without the square root. All right, here is a problem for you to try. The following amounts represent the ages of a sample of 6 employees currently employed at Ellison Enterprises. Calculate the variance and the standard deviation. So go ahead and pause the video and give this a shot. All right, that's all I have to talk about in this video, so I'll see you in the next one.